You know that air conditioner in your window or the fridge in your kitchen? They all work on tech that's like 100 years old. And here's the crazy part. The very thing we use to cool our world is actually making it hotter. So let's dive into a totally wild solution, one that isn't a gas but is actually hidden inside a solid crystal.
I mean, how wild is that? The idea that you could one day cool your entire house just by squeezing a solid block of something. It sounds like it's straight out of a sci-fi movie, right? Well, it's not. It's a real field of science called caloric cooling. And honestly, it's about to change everything we know about keeping things cold.
All right, so here's what we're going to cover. First, we'll look at the big problem with cooling today. Then, we'll get into this wild, solid-state solution. We'll even zoom into the molecular level to see how it works. After that, we'll see how it's going from the lab to actual prototypes, and finally, what the future of chill really looks like.
Okay, so first things first. To really get why we need a revolution here, you've got to understand what's wrong with what we're doing right now. Think about this. There are over 5 billion cooling units on Earth right now, and with everything getting hotter and economies growing, that number's set to almost triple by 2050. That's just staggering. And the craziest part? Pretty much every single one of them works the exact same way.
And this is it, the vapor compression cycle. It's probably familiar. You've got a refrigerant gas that gets squeezed, which makes it hot. Then it cools down, turns into a liquid, and dumps that heat outside. Next, that super chilled liquid expands, gets even colder, and then, as it turns back into a gas inside, it sucks up all the heat from your room. Boom, you feel cool. It's a clever cycle, and it's worked for a long time, but man, it has a serious hidden cost.
Yeah? The big problem? It's all about those refrigerants, specifically things called HFCs or hydrofluorocarbons. And when these things leak out, which, let's be honest, they always do, they are insanely potent greenhouse gases. We're talking a global warming potential thousands of times higher than CO2. It's basically an invisible climate disaster just humming away quietly in all our homes and cars.
So that begs the question, right?
What if? What if we could get that same cool feeling, but without using any gas at all?
This is where the story takes a sharp turn. We're leaving 100 years of old-school engineering behind and jumping into a brand new world of materials science. Welcome to solid-state cooling.
The whole thing is built on a principle called the Barocaloric effect. I know, it's a mouthful, but the idea behind it is actually super simple and kind of mind-blowing. All it means is that you can change the temperature of a solid material just by squeezing it and then letting go. That's it. No dangerous gases, no crazy global warming potential. Just a chunk of solid material doing all the heavy lifting.
Okay, so check this out, because this is the key to the whole thing. Your AC works by changing a substance from a gas to a liquid and back again, right? Well, barocaloric cooling also uses a phase change, but it's a change between two different solid states. The best way to think about it is with carbon. You've got graphite, like in a pencil, and if you apply an insane amount of pressure, its atoms literally rearrange themselves and it becomes a diamond. These new materials do basically the same thing, just with way, way less pressure. And when they change shape, they give off or absorb a ton of heat.
So, the big question is, how does this actually work? Like, down at the microscopic level. How can squeezing a crystal turn it into a little heat pump? Come on, let's zoom all the way in and check out the molecular machinery.
Okay, what you're looking at is a phenomenon called spin crossover. It only happens in some very special types of crystals. And in these materials, when you apply pressure, it's like flicking a switch on the electrons that are buzzing around a metal atom in the center. And when you flip that switch, the whole molecule is forced to change its size and its shape.
And this visual shows it perfectly. So at first, with low pressure, the molecules are all kind of big, relaxed, and messy. That's the high spin state. But then you apply pressure, and bam, they snap into this smaller, super organized, low spin state. And it's that change, going from messy to organized, that forces the material to release a whole bunch of energy as heat.
All right, so let's put it all together into a full cooling cycle. It's really just 4 simple steps. Step 1, you apply pressure. The material shrinks down and gets hot. Step 2, you get that heat out of there, just vent it away. Step 3, you release the pressure. The material instantly snaps back to its bigger, messy state. And here's the magic. Step 4. As it expands, it has to pull in energy from whatever's around it, and that energy is heat. That's what creates the cooling effect. Then you just repeat.
Okay, so that's the science, and it's awesome in theory, but how do you go from a cool molecular trick to an actual machine that can, chill a can of soda? Well, this is where the engineers get involved. So even though the refrigerant itself is a solid, you still need a machine to actually cycle it. This diagram here shows one way to do it. The easiest way to think about it is like a little conveyor belt that's carrying that yellow block, the solid refrigerant. The system moves the block into one area where it gets squeezed, making it release its heat. Then the belt moves it over to another area where the pressure is let go and it expands and soaks up heat. It's a really clever way to physically pump heat from one place to another. And we're not talking about a tiny little temperature change here. This effect is seriously powerful. Get this, research on something as simple as natural rubber showed a temperature drop of about 25 Kelvin. That's a 25 degrees Celsius drop. Or for us in the US, that's a 45-degree Fahrenheit swing. That is a massive temperature change from just squeezing something. It just goes to show you the huge potential we're talking about.
So let's put these two technologies head-to-head for a second. On one side, you've got vapor compression. It's been around forever, we know it works, but it's got that huge environmental problem. On the other side, you have barocaloric cooling. It has zero direct impact on global warming and could even be more efficient. The catch? It's still pretty new. It's just getting started, so its technology readiness level is still low.
But man, things are moving fast. I mean, the first real prototypes only showed up in the last 10 years or so. And look at this, by 2022, we had a tiny little fridge. A year later, in 2023, a device that could handle a wine cooler. And just this year, a prototype that can chill a single bottle. Yeah, the scale is still small for sure, but the speed of innovation, it's absolutely off the charts.
And you know what? That kind of rapid progress gets noticed. This tech is officially breaking out of the university labs and heading into the real world. We're talking serious investors putting serious money behind it.
One of the main companies you're going to want to keep an eye on is called Pascal. They actually spun right out of the research happening at Harvard. And their whole reason for being? To take this barocaloric tech to market and build the next generation of cooling devices from refrigerators to heat pumps.
And this isn't just a dream on a whiteboard. Pascal just landed $8 million in seed funding. Now that's a huge vote of confidence. It tells you that investors don't see this as just some cool science experiment anymore. They see it as a real, viable business that could totally shake things up.
You see, for a long time, one of the biggest roadblocks was that you needed these insane pressures to make the effect work. But here's the breakthrough, and it comes from Pascal's CTO, Jinyoung Seo. He says they've developed new materials that work at way lower pressures. And that's the whole ballgame, because now they can use standard off-the-shelf parts from the regular HVAC world, which finally makes this whole thing affordable.
Now, let's be real. They're not there yet. There are still some big hurdles. For one, they have to make sure these materials can be squeezed and released millions and millions of times without falling apart. They also have to figure out how to scale up from cooling one bottle to cooling an entire room. And finally, they have to make the entire system, all the pumps and pipes and everything, super efficient so we can really go toe-to-toe with the tech we have now. And that brings us right back to where we started. We're stuck in this crazy paradox, right? The very technology we use to make our lives comfortable is a huge problem for the planet. But what if the answer isn't some new, complex chemical? What if it's been hiding in plain sight this whole time, locked inside the beautiful, ordered structure of a solid crystal, just waiting for a little bit of pressure to unlock a much, much cooler future?